Welcome to part 2 of chapter 20, and today we'll be continuing some of the other topics related to the basic principles of intersection signalization. As we said last time, we already presented some of the main terms and definitions, and we also answered and defined what do we mean by discharge headway, saturation and flow, lost time and capacity, and also we defined what do we mean by the critical lane and time budget concepts. Today, this lesson we're going to be talking more about the delay as a measure of effectiveness at any intersection. So, there are several number of measures that have been used to characterize the operational quality of any signalized intersection. The very first measure is the delay. Delay is defined as the amount of time that can be consumed in traversing the intersection. Number 2 is queuing. Queuing is basically this is the number of vehicles forced to queue behind the stop line during a red signal phase. While number 3 is stops. How many stops? This really refers to the percentage or number of vehicles that must stop at the signal. So when it comes to the delay, to be more specific, there are several types of delay that we can experience as drivers crossing the intersection. The very first type of delay is the stopped time delay. Stop time delay can be defined as the time the time a vehicle is stopped in queue while waiting to pass through the intersection. While the approach delay really includes the stop time delay but adds the time lost due to the deceleration from the approach speed to a stop and the time lost due to the re-acceleration back to the desired speed. So this is basically again the added delay time when we are trying to decrease our speed if we see the light is red, or increasing our speed if the light turns from red to green. The third type of delay is the time in queue delay, which is basically the time or the total time from a vehicle joining an intersection queue to its discharge across the stop line on departure. The fourth type of delay is the travel time delay, which this one is basically the difference between the driver's expected travel time through the intersection and the actual time taken. While the control delay, basically that is the delay caused by the control device, either a traffic signal or a stop sign, and typically it's equal to the time in queue delay plus the acceleration and deceleration delay component. This is here to show you a schematic to show that there are at least mainly 3 of these delay types for a single vehicle approaching a red signal. As you can see, the x-axis is the time, the y-axis is the distance, and this line here shows the time versus distance if the light is green and the vehicle is gonna go through the intersection very smoothly. So this is basically the desired path. So the slope of this line will be distance over time, and that will be the speed. While again, if you are now approaching a red signal, you are gonna be deviating from the desired path to different other paths. So the very first line, D1, which is now I'm gonna I keep driving until I reach the intersection, and now it's red, and instead of now continuing on this path, now I will be having to I need to stop. This is the D1 is the stopped time delay, which is basically again the time that I will be stopping because of the traffic signal. D2 is now the approach delay. So what does that mean? Again, now once I reach this point, the red light is done. Now it's gonna take me a little bit of time to get back to the actual path, and now the difference between this dashed line, which was the desired path, and now the actual path, D2, that would be the approach delay, while D3 is really now the entire travel time delay, which is the entire difference between going through the intersection from a green signal all the way to a red signal. There are several theories behind modeling the delay. We will be talking about some basic theoretical models of delay, and we will be also try to explain this figure here, which is basically the time in the x-axis and in the y-axis we're going to have the cumulative number of vehicles. All analytical models of delay begin with a plot like what we see here, which is the plot of a cumulative vehicles arriving and departing versus the time at a given signal location. The time is divided into periods of effective green and effective red. As you could see here, we're gonna have here a green time, a red time, and then another green time. And as I said before, the slope, we're interested in the slope, which is gonna be the flow. And this is the desired path, but since now we're gonna have a red light, that means the line now is gonna start from here, and then there will be no flow, or the vehicles accumulated is going to be 0, or not going to increase with time until we hit the green light again. And now we're going to try to catch back to, or try to catch with the actual path again. So if we're having a constant flow like this line here, that means it's a constant slope of the arrival curve, while uniform arrivals assume that the inter-vehicle arrival time between vehicles is constant. So what does that imply? That if the arrival flow rate, for example, is 1800 vehicles per hour, then one vehicle arrives every 3600 over 1800, and that would be every 2 seconds. Every 2 seconds we're going to be having one vehicle arriving. More information, again, as I said, this is the time, and the y-axis the cumulative vehicles. This area here, the area under the curve, which is the shaded area, this is considered to be the aggregate delay in vehicles seconds. So why? Because the area here is basically the difference between the ideal case, which is this line, and the not so ideal case, which now including delay. And now the area between both of them are gonna be, again, the total amount of delay. Another information about the basic theoretical models of the delay, we typically start with assuming no pre-existing queue. That means vehicles arriving when the light is green continue through the intersection. And one of the examples is the departure curve is the same as the arrival curve. When the light turns red, however, vehicles now continue to arrive, but none depart. Therefore, the departure curve is parallel to the x-axis during the red interval. So that was, again, when the line now, instead of having a slope, it starts to be horizontal. What happens now once we have the green, when the next effective green begins, vehicles queued during the red interval depart from the intersection, now at the saturation flow rate S, which is in vehicles per second. For stable operations, the departure curve, which now try to catch up with the arrival curve before the next red interval begins. So if the two lines, or if the departing curve catch up with the arrival curve, that means it's a stable operation. And the only way of these two to catch up, that all the vehicles that they were standing and waiting while it was a red light, they will be moving, and the green light afterwards will be enough for all of them to leave, and therefore the two lines, the arrival time and the departure time lines, will be catching again. That means there is no residual or unserved queue left at the end of the effective green. This simple depiction of arrivals and departures at a signal allows the estimation of three different critical parameters. The very first parameter, which was the WI, this is the total time that any vehicle I spends waiting in the queue, and that would be WI. And basically this amount of time is given by the horizontal time scale difference between the time of arrival and the time of departure. The second critical parameter is the total number of vehicles queued at any given time, and that would be QT. And the way we get this total number of vehicles is the vertical vehicle scale difference between the number of vehicles that have arrived at that have arrived and the number of vehicles that have departed. So that's the difference. And the third parameter is the aggregate delay for all vehicles passing through the signal. And this is, as we said before, this is basically the area between the arrival and the departure curves. So it's going to be vehicles times time. So based on this, we can see now that there are three major scenarios or three conditions that we can have at any intersection. The very first one is a realistic, in any realistic condition. What happens in a realistic condition, we typically see a stable flow throughout the period depicted. That means no single cycle fails. What does that mean? That means every time the departure function at the end of the red light is gonna catch up with the arrival function again. So during every green phase, the departure function catch up with the arrival function. That means the total aggregate delay during this period is the total of all triangular areas between the arrival and the departure curves. So if you want to measure how much is the total aggregate delay, you will need to calculate the area of all these little triangles. This type of delay is typically referred to as a uniform delay. The second condition of one of the other realistic conditions is, in this case here, where we're having some of the signal phases fail at the end of the second and third green interval. Some vehicles are not served, as you could see, and they must wait for a second green interval to depart the intersection. How we would know this? As you could see here, for this green time and this green time and all the way to the third green time, it took us that much of time from the departure function to catch up again with the arrival function. So by the time the entire period ends, however, the departure function has caught up with the arrival function and there is no residual queue left unserved. As you could see, although here we have problems, for this cycle we couldn't catch up for this cycle all the way to here, but now when we reach this green light, the two lines are catching up again. So at the end of the analysis, there is no residual queue left unserved. This case really represents a situation in which the overall period of analysis is stable. That means, again, overall the total demand doesn't exceed the total capacity. The third case, which is now the worst case scenario that you want to see at any intersection, is now we're going to have additional delay to the uniform delay. That means now we're going to have a delay consisting of the area between the arrival function and the dashed line, which represents the capacity of the intersection to discharge vehicles and has the slope c. So now you see the departure line trying to catch up with the arrival function, but it couldn't. All over the place, even at the end of the analysis period, still there is a difference. The departure time or the departure function didn't catch up with the arrival function slope, and therefore we're having what we call an overflow delay. An overflow delay, that means every green interval fails for a significant period of time and the residual of unserved queue of vehicles continues to grow. As we see here, the difference between the departure and the arrival times keep growing throughout the analysis period. In this case, the overflow delay component grows over time, as you could see, and quickly dwarfing the uniform delay component. So now, instead of having the uniform delay, which is supposed to be, again, the area of these triangles, now we're having even a big difference between the departure time and the arrival time functions, and that's what we call, again, an over delay case. So based on this, again, we can have three different realistic conditions. One is uniform delay. That means all the vehicles queued at the red light, they are going to be fully served in the next green light. Or the second case, where we're having vehicles having issues and having extra delays a little bit, and they get served at the second green light. but eventually by the end of the analysis period, all the vehicles are served, all the way to this case here, which you see an overflow delay, where even at the end of the analysis period you still to see unserved vehicles that still need to wait for longer period of time to leave the intersection. So now the question would be, how can we come up with a component of delay? As we talked about in the previous three schematics, now in any analytic models for predicting delay, there are three distinct components of delay that can be identified. The very first one, that was condition 1, we have the uniform delay. The uniform delay is based on an assumption of uniform arrival and stable flow with no individual cycle failures. The second type of delay is the random delay. Random delay, now we're going to have some additional delay above and beyond uniform delay, because flow is being randomly distributed rather than uniform at isolated intersection. And the worst case scenario, where we're starting to have an overflow delay, which is now an additional delay that occurs when the capacity of the individual phase or series of phases is less than the demand or arrival flow rate. So you try your best as a traffic engineer to be having uniform delay at maximum random delay, but you want to avoid the overflow delay. So how can we in a schematic way to differentiate between uniform delay, random delay, and over delay? If you take a look at this figure here, now we could tell the difference between the three types of delay. The very first one, as you could see here, we're assuming we're having uniform arrivals, and therefore we're going to be having uniform delay. That means every car waiting in the red light is going to be served in the next green light. While we may have a more realistic case where we're having random arrivals, and therefore again I may see and I may need different or multiple green intervals to serve all the cars waiting, or where I can see here in some reality cases where now the platooned arrivals, that there is no theoretical solution available for this case, where we're having overflow occurring at this intersection, where I have lots of vehicles coming all of a sudden, and now we're gonna have what we call overflow delay. So how can we come up with some of the basic theoretical models of delay? So the very famous model that we typically use is Webster's uniform delay model. It's virtually you would see this model everywhere. It was initially published in 1958, and if you just Google it, you're gonna see it being cited for hundreds and hundreds of papers and published reports. And basically Webster's model is designed for uniform delay, which is basically the area under the curve, or the area between the arrival function and the departure function. So as noted previously, the aggregate delay can be estimated as the area between the arrival departure curves in the figure, as we could see here. So basically what you need to do, you would draw the x and y axes. The x-axis is the time, the y-axis again, as we said, the cumulative vehicles, and now we're going to have two lines. This is the desired line, or this is the departure line, and this is the arrival line, and the area under the curve would represent the amount of uniform delay, and that was what we call the Webster uniform delay model. Now to get into more of the math behind how can we get the area under the curve, the area of the aggregate delay have a triangular shape that is simply we can get the area out of it by having half of the base times the height. So as you can see, this is the simple first equation that was developed. UDA, which is the aggregate uniform delay in vehicle seconds, is simply an area of that triangle, half of the base, which is the length of the red phase, times V, which is the total vehicles in Q, and that's number of vehicles. So by convention, traffic models are not developed terms of red time, rather they try to focus on green time. Therefore, Webster tried to substitute the following equivalence for the length of the red phase. So the R, which is the red phase, can be now defined as C, the cycle length, minus C times 1 minus G over C. G is the effective green time over C, and that would be the cycle length. So if you do this, this is a good representation of the red time rather than measuring it in the field. So if you know the effective green time, divide this by the cycle length, 1 minus that ratio times C, that would give you the R, which is the length of the red phase. So therefore, again, the red time is the portion of the cycle length that is not effectively green. Now, how about the height of this triangle? The height of the triangle, which is V, is the total number of vehicles in the queue. It really includes vehicles arriving during the red phase R, plus those that join the end of the queue while it is moving out of the intersection, which is TC. Thus, determining the time it takes for the queue to clear that TC is an important part of the model. So the way we do it here, this is done by setting the number of vehicles arriving during the period R plus TC equal to the number of vehicles departing during the period TC. Or again, you can go through this analysis here. It's basically just following the curve or the figure that we talked about to get the area between the departure line and the arrival line, and we arrive to this equations here that we're gonna use in the next slides. So T sub C, this is R over S over V minus 1. The red light can be again estimated as this equation. And now let's take a look at how are we gonna use all these equations to simplify the model. So as we said, here he started to substitute for TC. We defined TC before. We're now going through some derivations here. So for the R, he replaced the R with C times 1 minus G over C, and the TC also was replaced. Therefore, if you go again through the analysis, the aggregate delay can be stated as this 1 over 2 RV. Again, we're going back to the main concept which is the area of a triangle, equal to half C squared times 1 minus G over C times VC over S minus V. And in order to get an estimate of the average uniform delay per vehicle, the average or the aggregate delay is divided by the number of vehicles arriving during the cycle, VC. Then that will give us the finalized equation right here. Another form of the equation that uses the capacity C rather than the saturation flow rate, which is S. This is the form, but you need to note that S, which is the saturation flow rate, is equal to C over G over C. So if you replace this value and the previous equation, we're gonna get this famous model UD, which is the average uniform delay per vehicles, equal to half of C, half of the cycle length, times 1 minus G over C. G is the effective green time, C here is the cycle length, over 1 minus G over C again times V over C. This is little c here is the capacity of the intersection approach, and the V is the arrival flow rate. So the uniform delay model assumes, as you could tell, assumes that arrivals are uniform and that no signal phases fail. That means arrivals flow is less than the capacity all the time during every single cycle of the analysis period. But what happens is, at some isolated intersections, vehicles' arrival are more likely to be random, Therefore, a number of stochastic models have been developed for this case, including those by Newell, Miller, and Webster, and those models try to assume that the inter-vehicle arrival times are distributed according to the Poisson's distribution with an underlying average arrival rate of v vehicles per unit time. Those models account for both the underlying randomness of arrival and the fact that some individual cycles within a demand period with v over c less than 1 could fail due to this randomness. So these are now the models for random delay rather than uniform delay. So the most frequently used model for random delay is Webster's formulation, which is this simple equation here: RD is equal to x squared over 2v times 1 minus x. RD, this is the average random delay per vehicle, and it's measured as second per vehicle, and x basically is v over c ratio. This formulation was afterwards, based on further information and further research, found that it's a bit overestimating the delay, and Webster proposed afterwards that the total delay, which is the sum of the uniform and random delay, must be estimated as this equation right here. So D, this is the sum of the uniform and random delay. It's equal to 90% of the summation between the uniform delay and the random delay. So to understand the models of delay, let's consider the following situation. An intersection approach has an approach flow rate of 1000 vehicles per hour, and it also has a saturation flow rate of 2800 vehicles per hour of green time, a cycle length of 90 seconds, and G over C ratio of 0.55. Now what we need to get is what's the average delay per vehicle is expected under these conditions. So we need to get the average delay per vehicle. So at the beginning of the analysis here, the capacity, which is V over C ratio for the intersection approach, must be computed. So this will determine what models are most appropriate for application in this case. So the way to get this is C is basically, as we mentioned in the previous slide, is equal to S times G over C. S, this is the saturation flow rate, which is 2800 vehicles per hour green, times the G over C ratio, which is 0.55 as mentioned in the example, and therefore the C, which is the capacity, is 1540 vehicles per hour. That means V over C, which is the X, capital X, that is used in the random delay equation, equal to what? 1000, which is the approach flow rate, over the estimated capacity, and therefore we're having V over C equal to 0.649. So what does this tell us? If the V over C is 0.649, that's relatively a low value. So because this is a relatively low value, the uniform delay equation, which is in your textbook equations 2019, may be applied directly. There is a little random delay at such V over C ratio, and therefore we're not gonna consider random delay, neither an overflow delay in this case, and the only thing that we're gonna consider is a uniform delay. So a uniform delay equation, as we talked about it before, D is equal to C over 2, which is C is the cycle length, 90 seconds, over 2 times 1 minus 0.55, this is the G over C ratio, over 1 minus 1000, which is the flow rate, over 2800, that's the saturation flow rate. And now this was give us the uniform delay is about 142 seconds per vehicle. As I said again, note that this solution assumes that arrivals at the subject intersection approach are random and platooning effects are not taken into account. So what happens now, let me ask you this, what happens if the V over C ratio start to get bigger? Let's say 0.8, 0.85. In this case now, besides this calculation, now we need to apply the RD equation, and then some RD plus this uniform delay, times 0.9, and that will be the total uniform plus the random delay for this problem. With this, we finish this chapter about the delay, and I want to thank you again for listening. Thank you so much.